This is the January 2022 Unit 6 Chemistry for Pearson Edexcel. So this is the used paper. Previously, I have made a video on the unused paper. So this is the paper that was used by the International A level. So let's begin. This paper is 15 marks, of course. I'll go straight to question 1. Question 1 says, a flow chart of a series of reactions of chromium and some of its compound is shown. So here we begin off with chromium. Of course, it's a solid in solid state. When you add dilute hydrochloric acid, of course, to chromium, they say you produce a blue solution. Chromium in blue, if it's colored blue, it means it's chromium 2. So this means if it's a blue solution, this is gonna be, could be chromium, hexa-aqua chromium 2+, that could be blue. Because this is dilute, it means there is some water in there. And then they say, standing in air produced a green solution. Of course, standing in air, oxidation, chromium 2 is converted to chromium 3 due to the oxygen in air. So that is oxidation. Of course, it's going to produce this still in air. And then next, we go to, they say, dilute ammonia was added. Usually when you have an hexa-aqua complex and you add dilute sodium ammonia, of course, it's going to be a deprotonation reaction. Deprotonation means, let me show you something like this. I know most of you know it, but imagine there are 6 water ligands all over. Okay. Now, as ammonia approaches, ammonia is going to be like that with its lone pair. As the ammonia approaches, actually, due to the difference in electronegativity here, this lone pair is going to be donated to that, and this goes away with that hydrogen producing ammonium, leaving OH here. So it means here, this was a water ligand, but a hydrogen has been taken away. It means we leave OH as the ligand left. So in this reaction, we will produce that plus 3 ammonium. If you had used 3 ammonias, if these were 3, you produce 3 ammoniums because 3 hydrogens have been taken away. So this is minus 3 hydrogens to create that. Okay, so this is basically, this is a gray-green precipitate. Of course, that is a precipitate, of course, of chromium 3+. And then they say excess sodium hydroxide. Of course, this is further deprotonation when you use excess sodium hydroxide to form a dark green solution. Of course, you guys know chromium 3 is going to be a green solution in excess sodium hydroxide or even in excess ammonia. But in excess sodium hydroxide, there will be further deprotonation. It can deprotonate further to produce that or to produce that. And here we have another step. This is chromium 3, of course. Here we see it was converted into a yellow solution. This is only due to oxidation using hydrogen peroxide, converting chromium 3 into chromate 6. And finally, when you add barium nitrate, we know barium nitrate is going to be soluble. When you add it to chromium and then you form a yellow precipitate B, it is because barium combined with chromate to form barium chromate. The other side, when we add sulfuric acid, of course, to chromate 6, of course, we're going to produce dichromate 6, which is going to be an orange solution. And finally, of course, this is a dichromate. Let's say dichromate. When you add alcohol to a dichromate, of course, you're going to form. This is going to be an oxidation. Ethanol is a primary alcohol. When you react it with a dichromate, it's going to be oxidized to a carboxylic acid, which is ethanoic acid. So this is the layout of the whole thing. However, let's go on to answer some questions that follow. So they say, give the formula of the complex ion of chromium present in A. I could say this is it, but they allow all these others because there are various possibilities. But for me, it's going to be hexa-aqua chromium 2+, because actually A was blue in color. The next part says, give the formula of the precipitate B. Again, let's go back a bit. Precipitate B, where is it? Here. After deprotonation, of course, it's going to be CrH, of course, 3 water ligands and 3 hydroxide ligands, correct? Identify reagent C by name or formula. What was reagent C used for? If you go back again, reagent C is here. It was used to convert the dark green solution into a yellow solution. Of course, if we know in this sample we have chromium, chromium maybe dark green being converted to yellow, that is using hydrogen peroxide as an oxidizing agent. And again, oxygen in air or oxygen in air cannot be used to oxidize chromium 3 to chromate 6, so that should be hydrogen peroxide. Next, suggest the identity by name or formula of precipitate D. Of course, that is barium chromate, because the barium nitrate reacted with something containing chromate, so a barium chromate, which is a solid. Next, they say state the color of solution E. Solution E, okay, of course, dichromate 6, that is going to be orange. And lastly, they say state the color of solution F. Of course, solution F is going to be green. The reason as to why that is going to be green is because you are having ethanol. You're reacting it or exposing it to a dichromate. So this is going to be orange. But the dichromate in this solution is going to be converted as you produce the ethanoic acid, CH3COOH. There is going to be a chromium 3 that is going to be produced, because this is going to be oxidized. Again, to use this is oxidation, and then this is going to be reduced. So the dichromate is going to be reduced to chromium 3. This is going to be green in color. That is why the final sample is going to be green, as we can see here. So this is the end of question 1. Let's go to question 2. This question is about the identification of 3 organic compounds, X, Y, and Z. A molecule of each compound has only one type of functional group. So it means each one has one functional group in each. Okay. So we continue. Each compound contains 6 carbon atoms and 2 oxygen atoms. In the mass spectrum of X, the molecular ion peak is at mass to charge 114. So we know if it contains, of course, 2 oxygens and 6 carbons, it means the 2 oxygens and 6 carbons are going to be 104. So it means we are looking for something that is 10, and that could be 10 hydrogens. So it means we're going to have 6 carbons, 10 hydrogens, and 2 oxygens. This is deduced from that. Again, we have, because they said, each in X, we have 6 carbons, and then we have, actually in each of them, we have 6 carbons, and then we have 2 oxygens. So, yeah, it should be 10 hydrogens. The next part says, 3 chemical tests are carried out on X when Brady's reagent. You guys know Brady's reagent is 2,4-dinitrophenyl hydrazine solution. When it's added to X, the orange precipitate is observed. Observation of an orange precipitate with 2,4-dinitrophenyl hydrazine means there is a carbonyl compound. That is a confirmation of a carbonyl compound. So X is a carbonyl. And then test 2 says, when X is heated with acidified solution of potassium dichromate, 6, no change is observed. It means, actually this confirms that if there is no change observed, it means there is no aldehyde. Yes, we already confirmed it's a carbonyl, but if in this case it cannot be oxidized basically, so this confirms that this is a ketone. And then we can see here the part 3 says, when X is added to an alkaline solution of iodine, of course this alkaline solution of iodine, this is the iodoform test, the formation of a pale yellow precipitate is observed. So it means X could have a CH3C double bond O group. Remember, we have confirmed it's a kind of a ketone, and which is a carbonyl that cannot be oxidized. Of course, and we know it's a carbonyl, it's a ketone, and it reacts with the iodoform. If it gives a positive test with the iodoform test, it means it has that group, and then something on the other side. So let's see. They say explain what can be deduced about a functional group present in X by considering the results in each of the tests. So I say test 1 confirms that X is a carbonyl compound. It could be aldehyde or a ketone. And from test 2, we can say X is not an aldehyde since it could not be oxidized by potassium dichromate. You guys know aldehydes are oxidized to carboxylic acids using potassium dichromate in acidified conditions. And test 3 says, test 3 shows that it has a CH3CO group, or you can just call it a methyl ketone group. So it should be a methyl ketone. So that's all we can say from that part. So I'll go to the next part. Says The high resolution proton NMR spectrum of X contains only 2 singlets. So we know it has 6 carbons. It has the hydrogens were actually 10. Let me see, 6 carbons, 10, and then 2 oxygens. We know it has a CH3, it has a CO, and somewhere here. So they ask us how many environments there were. Let me see. Okay, it has only 2 singlets. If there are only 2 singlets, it means we can be able to get it, I see. And they say there are only 2 singlets with relative peak area 3 and 2. So basically, in one environment, in fact, this is relative peak area 3, 2. It means that is a ratio of one environment to the other. So let's see. They said draw the structure of X identifying the 2 proton environments. So these are 6 carbons, and we have this side, and there is another oxygen the other side. If you position the other carbons, 1, 2, 3, 4, 5, 6, it means this one should have a CH3 on the other side because it's at the end. We already used up 6 hydrogens, so it means these ones cannot be fully formed. They cannot fully be all alkyl, maybe CH2, CH2, CH2s. It means there is going to be possibly another oxygen there. So maybe this is a dimethyl ketone. So on both sides. So as you can see the structure here, and again to go to the ratio, the peak area ratio, if it's a 3 to 2, it could actually mean in one environment there are 6 and in the other environment there are 4. Remember, this is just a ratio. A ratio is just giving you the whole number ratio of the 2. It could be the real value could be a multiple of those. So when you look at the structure I deduced here, you can see this environment here is the same as that environment. And the total protons in here are 6 protons. Yet this environment is the same as that. In here we have a total of 4 protons. So the ratio of environment one to the other is going to be basically a 6 to 4, which comes out as a 3 to 2. And another thing we can see is, remember they said we have 2 different environments. Actually, when you look at this environment here is going to be a singlet, and the other environment is a singlet. So here we can see 2 environments, A and B, and the structure is going to be like that. Here I further broke it down to show you. The formula of Y is carbon 6, hydrogen 12, or 2. When aqueous sodium carbonate is added to Y, when you add sodium carbonate and effervescence occurs, and the compound you're adding it to is organic, that means there is an organic acid, of course, that is a carboxylic acid. So if we are looking for, they say, identify by name of formula, the functional group, this functional group is going to be the carboxylic acid functional group, which is basically that. Next part says the carbon-13 NMR spectrum of Y contains 4 peaks. Remember, this is this compound here has just a minute. It has 6 carbons, hydrogens are 12, and oxygens are 2. If they say it has 4 peaks, it means it has 4 different carbon environments. The only possible structures are this, and let's see why this is the case. This is, when you consider this structure, this is environment 1 that is identical to that, and that these 3 are identical, then this is going to be your environment 2, environment 3, and environment 4. So we have 4 different carbon environments. There is no other way you would arrange it except these 2 structures. So here we have 4 different carbon environments, and in here we have environment 1, which is identical to that, environment 2, which is identical to that, and environment 3, as well as environment 4. We can see again, these here we have 4 different environments. There are no other structures except only these 2 here. So those were the possible answers. Next says, explain how the low resolution, here we are looking for low resolution, meaning there is no splitting. Low resolution proton NMR of Y would confirm which of your structures in D3 is correct. Chemical shifts are not required. If we are looking for low resolution proton NMR, so let's see structure 1. As we can see, structure 1 would have 3 peaks in the basically low resolution proton NMR for protons. Let's see. Again, I'm going to erase the purple colors so that we can look at, those were carbon environments, so let me remove them so that we can look at the proton environments and see if they are identical or not. Remember, we are looking at the difference between the proton environments, why some of these protons, why they would have different proton environments. Let me finish this up. Okay, so let's use another color, red, to see. So here, proton environments, these are all identical. The protons on all these carbons are going to be identical. And these protons here are going to be identical as well, because they are in the same environment, and that is going to be, so here three proton environments. Okay, and let's see the other side. The other side again, let's see, we have that proton environment is identical to that proton environment, and then this proton environment is identical to that proton environment. Then this proton environment is unique, and that proton environment is unique. So we have four different here proton environments. So the difference between their their hydrogen L proton and NMRs would be, this would have 3 and that would have 4. That's the difference. So here I say structure 1, which is 3,3-dimethyl butanoic acid, would have 3 peaks, and structure 2, which is 2-ethyl butanoic acid, would have 4 peaks. So that is the difference between the two. Let's go to the next part. The next part here, we are dealing with the last structure, which is Z. It's carbon 6, again hydrogen 12 O2. They give you the infrared spectrum of Z as here. And of course, you guys know usually we ignore that, the other side, which is the fingerprint region. Usually after 1500, we ignore it. So we're going to focus on this peak here and that peak there, because they are standing out. So, okay, that is Z. And if we can see, we have, they gave us here basically the table of wave numbers, and I'll go to the first question, the next part. They say Z has a fruity smell. Fruity smell confirms ester. It's an ester. So they said deduce the identity of the functional group present in Z using all the information given, and include any relevant wave number ranges in your answer. So here I said it's the fruity smell indicates that Z is an ester. However, we have to go back to the peaks and be able to identify. So, okay, we have a peak here. Let's go to that. Ester, where are the esters? Yep, ester, only the information they give us is 1750 to 1735, which is actually there. So we can use this. It's an ester because it has a peak at 1750 to 1735. That is confirmation of an ester. So that is why it's for the carbon oxygen in an ester. All right, the next part says the high resolution proton NMR spectrum of Z contains 4 peaks, J, K, L, and M. Peak J has the highest chemical shift, showing that this proton environment is close to an electronegative atom. So they showed us the splitting pattern of the peaks in this table. Like see, they say I'd rather displayed formula of Z, labeling the proton environments responsible for each. We already know that this is going to be an ester, so we can begin by positioning. Of course, an ester should have a CO, O, a carbon the other side, and of course something this side. It could be a hydrogen this side, but it can be anything. However, this one here has carbon 6, hydrogen 12, and O. So, and they told us it has 4 different environments. So it means we're gonna have K. So proton environment number 1, of course, there should be a CH3 because this side. And then if this side we have a CH3, let me see, CH2, CH3. You can begin by positioning the hydrogens and see if they make sense. Let me see, 3. So these we have 5, and the other side we have 5. That is going to give us, no, it doesn't make sense because even the carbons are not yet 1, 2, 3, 4, 5. So it means we should have 1 here, another carbon attached to this, which gives us, of course, CH. This is going to be a CH3. And that is something like that. In this case, this and these are identical environments. So we have environment 1, environment 2, environment 3, and environment 4. And we can further confirm and see, because they've told us there is a septet, meaning there is an environment that has 6 protons. If it's a septet, using the n+1 rule, it means one environment has 6 protons in it. So this is confirmation of the environment, sorry, the environment with 6 protons, which is basically environment, one environment. So this one has 6 protons. There is another environment that is we have a doublet, meaning it's next to an environment with 1 proton. And then so basically, if we look at it, this is going to be a doublet. This is going to be a septet. This is going to be a doublet. and this is going to be a quartet, where this is going to be a triplet. It's a triplet because based on the n+1 rule, the neighbor has only 2 hydrogens, but n+1, 2 plus 1 gives a 3, so it's going to be a triplet. And so this one here is a triplet, but for this one here, we know the neighbor has 3 protons. Using the n+1 rule, 3 plus 1 becomes 4, so that's why it's a quartet. We use the same rule, and actually you can see that J, which is a septet, is going to be the one that has next, that is basically next to the one with 6 protons. So this is J, and let me see which one is a doublet, which is going to be L, and the one that is a quartet, okay, it's going to be K, and the one that is a triplet, it's going to be M. So this is M, that is K, and this is going to be J, and that is going to be L. So this brings us to the end of question 3. A student investigated the kinetics of the reaction between bromide ions and bromate ions. So this is the equation for the reaction, of course. So the first step says, to determine the rate equation for the reaction, the student varied the concentration of bromide, bromate, and acid in turn. The effect of the concentration of bromide ions was investigated first. Procedure is step 1. They say add 10 centimeters of 0.005 mole per decimeter cube potassium bromate. 5. 15.0 centimeters cubed of acidified methyl orange indicator solution, and 5.0 centimeters cubed of 0.0001 mole per decimeter cubed aqueous phenol to a beaker labeled P. Prepare the contents of the beaker Q for run 1 as specified in the table, and pour the contents of a beaker Q into beaker P and start the timer. Pour the contents of beaker P back into beaker Q and place the beaker Q on a white tile. Of course, a white tile is going to help you to observe clearly. Stop the timer as soon as the mixture turns colorless. Record the time along with the temperature of the solution. And then they say repeat step 1 to 4. So here we see what experiments were carried out from run 1 to run 7, varying the different concentrations of the potassium bromide. So let's go to the real questions. The first one, they say give one reason why the contents of the beaker P are poured back into beaker Q in step 3. Let us see step 3. Step 3, they say pour the contents of beaker Q into beaker P and start the timer, and then pour the contents of beaker P back into beaker Q and place beaker Q on a white tile. This is mixing. They are trying to make the reactants mix properly in order for the reaction to continue well. Then they say methyl orange indicator is bleached colorless. Now this is very important. Methyl orange indicator is bleached colorless by bromine. Under the experiment conditions, the reciprocal of the time taken for the methyl orange to be bleached is going to be this, is proportional to the initial rate, and they want you to explain why phenol is added to the reactant. Of course, phenol reacts with bromine so that it delays the color change, or again, I put for you some explanation here. So the reaction occurred like this. This is what we were looking at. Let me use another pen. This is what we are looking at. So when phenol is added, phenol will react with the bromine, because remember, bromine is produced by this reaction. So the phenol is going to react with the bromine as soon as it's produced in order to basically reduce the amount of bromine present, so that the methyl orange will only react with the leftover bromine, and then the color change will be observed. So basically, phenol is just helping us to delay the color change by removing. So basically, by removing bromine, it delays the reaction between bromine and the indicator, so that the color change is going to be delayed, or bleaching will not occur faster for us to conclude that the reaction is done when actually it's not. I'm going to let you observe this clearly. This is my explanation for that step in words so that you can be able to fully get it. So let's go to the next part. They say give the color of the reaction mixture before it turns red. Of course, it's going to be pink. They also accept red, but it's going to be pink. Give the reason why the temperature is measured in step 4. Let's go back to step 4 a bit. Step 4, they say stop the timer as soon as the mixture turns colorless and record the time along with the temperature of the solution. The reason for this is, of course, temperature has to be maintained constant. So if the temperature is not constant and it's increasing or decreasing, it means the reaction can be affected. You guys know rate of reaction is affected greatly by the temperature. So we need to ensure that the temperature remains constant in order for our results to be valid. The next part says the student results are shown. So these are the results of the experiment. So they say complete the table by drawing the remaining values of 1/t. I used my iPad to draw this, so the lines may not be, of course, that straight, but it's okay. It's a good one. So let's see. We have the y-axis, which is going to be 1/t, and the units are per second. Get a good scale. And then the x-axis is going to be volume of potassium bromide in centimeters. Ensure that this line goes through the origin, and then draw the line of best fit, passing through the possible points, of course, again through the origin. And then let's go to the next part. It says, state why the volume of potassium bromide is proportional to the concentration of bromide ions in the reaction mixture. So here, what we have to know is the total volume of this solution in the reaction flask has to remain constant. So it means if it has to be maintained to 10 centimeters cubed. So the volume of potassium bromide will, when you decrease the volume of potassium bromide, the concentration of the bromide ions are also going to decrease. So when they ask state why potassium bromide is proportional to the concentration of bromide ions in the reaction mixture, it is to make sure that the total volume of the liquid in solution in the reaction flask is going to remain constant. That is why it has to remain constant. And then next it says state the order of reaction with respect to the bromide ions using your graph. When we look at the graph, again, going back there, a straight line. Remember, again, this is a rate over, of course, called rate over, I would say this is volume, but of course it's going to be concentration, of course. Rate over concentration graph, if it goes through the origin like that, that is going to be first order. If it goes like that, or if it goes like this, it's going to be zero order. If it goes like that, it could be second order. But of course, ours through a straight line through the origin, it's going to be first order. Again, I said this is against concentration because remember, volume is constant. If you are varying the number of moles and the volume is constant, or it means it's the concentration that is basically changing. So it's kind of the same. It's like a rate concentration graph. So this is going to be first order with respect to the, of course, bromide ions. Next says, after investigating the effects of the rate of the concentration of bromide 5 ions and the concentration of hydrogen ions, the student obtained the graph shown. So this is also a rate against concentration is going to be first order, and this is rate against concentration that is going to be, let me see, this is concentration squared. Be very careful about it. When you get a rate against concentration and you get a curve like that, usually you can carry out the experiment again, or you could do it again and you could plot your results again and get a rate against concentration squared. If it's a straight line through the origin, then that means this is second order. So this one here, because it has a square, it's going to be second order with respect to hydrogen ions. This is first order with respect to bromide 5. So the rate equation is going to be rate is equal to K. Remember, it was first order with bromide. It's first order with bromide 5, and it's second order with H+. So this is the rate equation that results. This brings us to the end of question 4. This question is about the preparation of phenylamine by the reduction of nitrobenzene. Okay, reduction of nitrobenzene to produce phenylamine. Of course, here we use tin in the presence of HCl to convert a nitro into an amine. So they say outline of the procedure. They say step 1, add 2.1 centimeters cubed of nitrobenzene, 5 grams of granulated tin, and 10 centimeters cubed of concentrated hydrochloric acid to a round bottomed flask. This HCl has to be concentrated. Add a few anti-bumping granules to the flask and heat the contents under a flask. Adding anti-bumping granules promotes smooth boiling and, of course, so that they do not spit out. For 15 minutes and leave to cool. Dissolve 7.5 grams of sodium hydroxide in 10 centimeters cubed of distilled water and add to the flask. An initial precipitate forms before dissolving. Then add 15 centimeters cubed of distilled water to the flask and steam distill the contents, collecting the cloudy distillate in the conical flask. Then they say add 3 grams of powdered sodium chloride to the distillate and swirl to dissolve before transferring the contents to a separating funnel. So this is basically a kind of purification. Add 8 centimeters cubed of ether to the funnel. Of course, this is going to be the solvent. And check or occasionally relieving the pressure. Relieving the pressure, of course, and allow the layers to separate. So this is solvent extraction. Then step 6, discard the aqueous layer before transferring the ether layer. So ether was the solvent that extracted the organic component or organic liquid we're interested in from the reaction products. So transfer the ether layer to the clean flask containing a few pellets of potassium hydroxide, and then decant the contents of the flask from step 6 into a pear-shaped flask and distill off all the ether. Distill the remaining contents of a pear-shaped flask, collecting the fraction, boiling between 180 to 185. So this is the information we have here. They give us the chemical, the hazards, and then the molar mass, the density, and the boiling temperature. So we can go straight to the questions. The first one says, give reasons why gloves should be worn. You're working with nitrobenzene, which is toxic, and actually you have concentrated hydrochloric acid, so you have to use gloves. Concentrated hydrochloric acid is corrosive, and nitrobenzene is, of course, toxic, so you have to use gloves. State the role of tin in the preparation. Tin is a reducing agent. You guys know we use tin with HCl. Actually, in the reaction, these two react together to produce the hydrogen that is going to be basically used in the reduction. Suggest by name or formula the identity of the initial precipitate in step 3. Now in here, the initial precipitate is going to be tin 4 because actually tin is going to be oxidized. So tin 4 hydroxide is going to be the initial precipitate. Okay, or you could say tin 2, so it's going to be tin 2 and then tin 4. State why the distillate in step 4 is cloudy. The distillate is cloudy because you're going to have an organic compound that is slightly having some water in it. So because it's a distillate, you have some water in an organic compound, so it makes it to be cloudy. So phenylamine in water. The question D says, suggest why sodium chloride is added to the distillate. Sodium chloride to the distillate. Sometimes when things are not separating properly, when you have an aqueous and organic layer that are kind of more miscible into each other than you want to, it means you cannot break them or separate them into layers. So you add salt. Usually sodium chloride is added to kind of increase the ionic component or ionic content of the aqueous layer in order for it to separate fully from the organic layer. So here it's easy to separate, to help separate. It helps separate the layers, basically. That is called salting out when they separate the layers due to increasing the ionic content of the aqueous layer. Draw a labeled diagram of the separating funnel at the end of step 5. At the end of step 5, again, we can go back here and see step 5. They say step 5. Add 3 grams of powdered sodium chloride to the distillate and swirl the distillate before transferring the contents to the separating funnel. Add 8 centimeters cubed of the ether to the funnel and check. Now we have 2 layers. One is going to be an ether layer and the other is going to be, of course, the aqueous layer. To take you back to the content we have here, remember the ether is here, the density of the ether is 0.71 and the density of water is 1.00. So the aqueous layer is going to be below the ether layer. So when we draw the separating funnel, the organic layer is going to be above. The organic layer contains the ether and the product. So because it's going to be ether containing the product, so it's going to be high because it's the solvent, and then this is going to be the aqueous layer. So the next part says, state how you would relieve the pressure in the separating funnel in step 5. To relieve the pressure, you use your thumb to tap the top part of the separating funnel and then invert the funnel. As you invert, then you open the funnel, or you open the top of the funnel in order to basically relieve some pressure. You invert and then open the top in order for the pressure building up to be released. Next part says, suggest one reason for adding pellets of potassium hydroxide in step 6. Potassium hydroxide in this case is going to be for basically drying or to absorb water. You guys know they can to absorb water so that it's kind of going to be kind of dried. Next part says, state how the mixture would be heated to distill off the ether in step 7 and justify your answer. Then when we go back, I want us to go back to the contents in the table here. They told us the ether is actually highly flammable. It means you cannot heat it using direct flames. You have to use an electric heater. So again, here we can see I said using an electric heater to heat because the ether is very flammable. Next part says calculate the mass of phenylamine formed in this preparation. They said the limiting reagent is nitrobenzene and the overall yield by mass is 43. So if they say it's the limiting reagent, it means all the nitrobenzene got finished. So it means the tin and HCl were in kind of excess. This was in excess. This was limiting, so limiting. And they gave us a yield of 43%. If you go back to the beginning, the volume of the nitrobenzene used was 2.1 centimeters cubed. So I can begin from there. Mass of nitrobenzene using the density from the table of nitrobenzene. Mass is going to be density times volume, which is basically 1.2 times 2.1, which gives us that as the mass. Now, when I have the mass of nitrobenzene and I have its molar mass, I can find the number of moles using mass and molar mass, and those are going to be the number of moles. Of course, you can use a calculator of this. Then now I know the mole ratio is 1 to 1, so it means the number of moles of nitrobenzene are going to be exactly the number of moles of phenylamine. These are theoretical moles. And then since we have the number of moles of phenylamine and I have its molar mass, I can be able to find the theoretical yield or theoretical mass here. Number of moles times molar mass, which is that times that, gives us this. So here, this is going to be the theoretical mass. So I know that experimental mass is going to equal to yield times theoretical. Of course, theoretical, I'll say here, this is going to be the yield, actual mass, so theoretical mass, divided by 100, which is going to be 43, divided by 100 times 1.905, and it gives me this. And this is going to be, of course, the mass of, this is going to be the mass of the product or the actual mass that was yielded during the experiment. This brings us to the end of this paper. This paper was the January 2022 Unit 6 Chemistry for Pearson Edexcel, the used paper. See you in our next video. Thank you.